on the spacecraft. Mine is one of two that are inside the analytical laboratory. So when the thing's going around on Mars and looking at stuff, there are mast instruments that take pictures of things. There are arm instruments that just put a thing down on the rock or drill a rock. And then my instrument, CheMin, is actually inside the body of the rover. And the sampling arm and drill would deliver a small powdered sample to me, and then I would analyze it. And so what CheMin does is it's the first instrument ever to land on Mars that will give you the mineralogy of Mars soils and rocks for the first time. So that's what we hope is going to happen on the 6th of August or soon thereafter. Now, I have some slides to show you exactly how the instrument works. And then I have one of our field instruments here in the orange box, and I'm actually going to run some analyses. And I sort of know what these are, so I won't be stumped by the answer, but I'm going to pretend I don't know, and I'll show you how CheMin would analyze these things on Mars, and I'll show you how the instrument works. So first of all, let's go to the first slide here. And this is, it gives you definitive mineralogy of Mars soil and rocks. It uses a technique called X-ray diffraction. And X-ray diffraction is actually not a new technique. This actually next year when Curiosity lands on Mars is the 100th anniversary of the invention of X-ray diffraction. So it's a big deal for mineralogists and diffractionists. It'll identify all the minerals present in soils and rocks. Now, why is that important? Minerals are phases, and they're stable only under certain conditions of temperature and pressure and chemical things around them. And the result is, if we know what the minerals are in a rock or in a soil, we can tell you what the environment was when they were formed. And that's exactly what we want to know. When we go to Gale Crater, we want to know, when we land there, what was the condition there? 3.5, 4 billion years ago, was there a lake there? Was it a river? Was there no water at all? We don't think there was no water at all, but we will know from the mineralogy. So next slide. Okay, so we use X-ray diffraction for mineral characterization. We also do X-ray fluorescence, which tells you what elements are present in the minerals. And there's only a single detector for this. It's a CCD, just like the kind of thing that's in your camera. There's no moving parts. And the only moving part of the instrument is actually a wheel that rotates the sample into position. Everything else doesn't have to move. Next slide. Okay, so here's the instrument. There's basically an X-ray tube here, just like you might have when you get your teeth X-rayed. There's an X-ray beam. There's a little pinhole collimator, and it makes a little tiny pencil beam that's about 70 microns in diameter. It's smaller than a human hair. And the sample sits here in a transparent cell. And the grains inside this transparent cell are rotated around and moved by sound. So we actually have a little vibration system that you'll hear it when I run the sample. You'll hear it whistling. And these grains move around in the beam, and diffraction occurs with the crystalline materials, and they form these rings. And these rings, when we bring these images down to Earth, we form these one-dimensional things called diffractograms by looking at the intensities going outward from the central beam. And these diffractograms will tell you the minerals present and how much of each mineral is present. It's absolutely definitive, and I don't want to say it's foolproof, but it's close to it. Okay, let's see, next slide. So here's an example. This is actually from the flight instrument. This is one 10-second exposure of a CCD frame. This CCD is 600 by 600 pixels, so it's a really small sensor compared to what you're used to in your kind of cameras, but it detects X-rays directly. And it not only detects the X-rays, but it measures their energies. Each one of these little pixels in here measures the energy of a photon that strikes it, individual photons. So out of this 10-second frame, over here you can see we're starting to see these rings. Well, this is a particularly strong diffraction. This is quartz and beryl. That's one of our standards. Very strong diffraction. You can actually see these rings developing in 10 seconds of analysis. And this is the 2D or 1D scan here. And these peaks although there's a lot of noise here. These peaks, I could analyze this and tell you this was beryllium quartz. And then if you look down here, if you take the energies of all these photons that struck this detector and display them here, you can see this is cobalt. That's the actual X-ray beam that comes out of the tube. And then we've got chrome. There's a little argon from the atmosphere, silicon, aluminum, and so forth. And this chrome, now this barrel, they wanted to make sure it was exactly perfect, so we had to use emeralds. It's one of the reasons why the machine was, it's not really the reason why the machine was expensive. But we were told we had to use gem quality emeralds to make the crushed material for this. And the coloring agent in emerald is chrome. So that's 3/10 of 1% chrome that was in that material. OK, next slide. So we take maybe 100 of those individual frames and sum them up. And you can see we're starting to get a pattern here. And then we take about 5 or 10 of those 100 frame sets and make one major frame. And that becomes an analysis. And that has very low noise, and it's very easy to tell from that what's present. Next slide. And we developed a number of prototypes for this machine. This is actually what we called CheMin 4. That was our first, what we called portable, but it just about killed us dragging it up the mountain, so it wasn't that portable. And this is up in Spitsbergen, Norway, 80 degrees north. And it was the first analysis in the field by X-ray diffraction. Next slide. So from that, we started developing other instruments. And actually, some of these are, the thing I'm showing you here is actually a commercial instrument that was developed by a company that one of my postdocs actually started. And so this is what we called, it was originally called Mini CheMin because it was supposed to be smaller than CheMin. They called it Terra. And then this was one that we had that went in robotic vehicles that we called Roboterra. And this was a reflection instrument that was made for the Getty Museum for looking at artworks. And next slide. And then this just shows some of the, this is up on Mauna Kea for a in situ resource utilization experiment for lunar stuff. This is in the dry valleys of Antarctica. This is up in northern Canada, and this is again in Spitsbergen. Next slide. Well, this is in the Utah desert. But people wanted to try this to see if an astronaut with gloves could use it, and they sort of could. This is 7 kilometers down in a potash mine in New Mexico, and they needed to know which way to dig, and otherwise they'd have to assay the ore out of the mine in a different county. And we're also using this to analyze lunar rocks. You'd be surprised, there's still a lot of research being done on lunar rocks. This is Jeff Taylor at the University of Hawaii, and we're analyzing 100 lunar soils with this, and they're going to be the baseline data for orbital missions to the moon. OK, let's stop for that right now. And I kind of wanted to give you a flavor of it. Now I'm going to really show you the machine. And this really is what I wanted to show you. This was just kind of like an intro. So this is functionally identical to the thing we're sending to Mars. The difference is that there are commercial components in here. When I put a sample in, I put the sample in. It's not a wheel with an automatic gizmo. And when I prepare a sample, I don't have the real fancy arm with the thing, so I've got a hammer. And this is called a percussion mortar. I sent this all over the world with my little kit, and I had to describe all the components through customs. And the first time I called it a percussion mortar, I had serious issues. So I just called it a sample preparation device after that. So anyway, this is, we've been all over the place with this. It's battery powered, it's wireless, so I'm actually communicating it wireless with this thing, this computer. And let me show you how I prepare a sample, and then I'm going to show you the nuts and bolts of what an observation looks like. So first of all, I went all over in front of the Hilton trying to find rocks, and there's just no rocks in this. There's no rocks in Florida, I'm pretty well convinced. So I've got some beach sand here. I've got a couple of seashells, and I've got an aspirin tablet. So I'm going to start with the beach sand. And I'm not sure how fine-grained this is, so I'm going to grind it up just a little bit. So I'm just going to put some beach sand in here. Whoops. My apologies to the custodial staff. And I just want to make sure there's enough fine-grained material to analyze. Let's try this. Now this is a 150 micron sieve. This is the same diameter sieve diameter that is used on MSL. So I'll show you what this looks like after I'm done. You can see how small the holes are. And just for scale, a human hair is about 100 microns. So the holes are about the size of a human hair in diameter. 100 microns, yeah. Well, no, this is 150. And there's two kinds of ways to hit things. There's whacking and there's thwacking. And so whacking is when you just really whack something. Thwacking is you give it a sharp rap. And that's the kind of thing that works for, for things like this. And there's actually kind of a joke that there was what they call a critical design review for the sample preparation equipment for MSL, and it lasted 3 days, and everybody was just dead tired. It was 6 at night on the third day, and the guy who was answering questions, basically somebody asked him. He said they were thwacking, and somebody asked him the question, what's the difference between whacking and thwacking? And he basically said, I'll tell you the answer to that, or I'm going to show you the answer to that if you ask me another question. I think that was pretty close to the end of the review. Okay, so there's a little bit of material, and you almost can't even see that in there, but that's really enough to do an analysis on this machine. So that's right, yeah. Even though they're going to make grams of material on MSL, we need the amount that's about the size of a baby aspirin tablet. That's how much we need. Yeah, and I'll show you that. This is so let's see. Let me start the vibration. It's the actual machine going to Mars is about a 10-inch cube, and this one is better than it's worse. It's better because we don't have to have that big sample wheel with all the things on it. It's worse because we carry our own power. So the spacecraft provides us with power, on Mars, but for us, we power with laptop batteries. So these are pretty heavy in their own right. But this thing is pretty well packed solid inside. So what you're hearing is this works very similar to the sample holders on Mars. It looks a bit like a tuning fork. There's two sides, and there's a piezo vibrator in the middle that vibrates at the resonant frequency of this tuning fork, and that causes the material in there to move around and like a liquid. Okay, so it's a pretty clever device. My colleague Philippe Sarrazin was the one who figured this out. And this actually got NASA Commercial Invention of the Year this year. And I was thinking it really ought to be something like a tricorder or something. I don't know why a thing that just moves dirt around should merit that, but whatever. Okay, so what I'm going to do is I'm going to take a little bit of the material. And this is unlike MSL. And let's see. So I'm just going to put it on a little spatula here, and I'm put it right in this hole. And this is what would be coming down that little funnel and into the sample cells in the machine. And this is this is like an external shaker, so that we can see what's going on to make sure the sample is good. So I just put this in here, and I don't know if you can see the grains running around in there. You can certainly come up later on and take a look, but believe me, they're kind of going in circles. And the noise you hear is actually it's ramping this piezo through about 2,000 hertz, which is the resonant frequency for this tuning fork. And then when it gets a resonance, it really shakes hard. So, okay, I'm going to put this inside here. And I'll stop this thing. Okay, and now I'm going to command it from here. I'm going to just tell it to, and once I command it to start going, I'll turn this around so you can see it start acquiring the data. So let's see here. I'm going to call it quartz. I'm not supposed to know what it is, but I'll just call it that. I actually thought, when I started out, that there was carbonate. You know, I thought it was a carbonate sand, and I think that what the deal is on the Gulf Coast it's carbonate, and on the Atlantic Coast it's silica, quartz.
We have Coquina Reef off the shore here, which is a shell rock.
Oh, okay, okay, and that would be calcite or a carbonate.
Well, you tell us.
Well, I'm gonna. Well, that would be okay. It would be. It would actually it'd be probably a ragonite, which is what the shell is, which I'm not supposed to know either. But I'll I'll tell you. Okay, so start the analysis, and should start humming here pretty soon. Okay. So it finds resonance, and then it starts shaking right around the resonance frequency. And now it's starting to take analysis. And let me see if I can find it here. Okay. Okay. So it's not showing anything right now. You should see the first little pattern pop up. This is about 4 times faster. So we kind of juiced this one up a little bit because we could. We didn't have to answer to JPL for the power. Okay, there we go. So that's 10 seconds of data. And I can tell, because I know this, that the quartz, strongest quartz peak is at 30.5 right there. So I could tell you right now that's quartz, just from that one peak. But it collects data and shows it to you as it's doing it. Now, we can't do this on Mars because obviously we have to wait for the acquisition and then link up to the satellite and all that. So we won't know for a day. We have to tell it to analyze for 5 hours, and then we get 5 hours worth of data. But in the field, if I can figure out what something is in 10 seconds, I move on, you know. So, oops. Okay, so I'll show you how to analyze this, and maybe I'll just, if I kneel down in front, would that be good, or maybe I can do it upside down. Let's see. Should I turn it this way? Okay, and here's what I can do. I can go right here. Okay, so there's now that's now 5 exposures of 10 seconds each. That's 50 seconds of exposure. And what I'm going to do now is I'm going to take this data. Let's see. Take this data and pull it down onto this computer. So right now it's resonant on this machine. And as soon as I collected, as soon as I, let's see, processed, as soon as I download it, then it's resonant on my computer, and then I can use the programs on my computer to do the analysis. So it just simply takes what you saw on the screen. Now it's going to open up in a commercial package called Jade. And it should open up as a pattern here. There's the pattern. Now, normally I'd have to subtract a background. This is a pretty low background, so I don't really have to worry about it. But let's go to Identify, Search Match Setup. And I have a full, now the difference between minerals and inorganic materials is there are hundreds of thousands of inorganic materials. There's only about 4,000 or 5,000 known minerals on the Earth, so there's only 4,000 or 5,000 to choose from. If there's something that we don't know that isn't a mineral that occurs on Mars, we'll still be able to find it out. It'll be an inorganic compound that's unknown on the Earth, and we'll just name it. We'll know what we'll name it. We'll be the guys who name what it is, and it'll be a new mineral. So This is called the International Center for Diffraction Data, powder diffraction files. And there's like, they have a list of all the minerals that are present. And so all I have to do is go search match. And it'll look through all those files and figure out what fits. And it finds quartz. So there's quartz. And let's get rid of everything else. And then I'll go back to do a quantitative, well, it's a single phase quartz, so there's no reason to do quantitative analysis. But let me just do a quick refinement to see if there's anything else there. Okay. Let's see, full with half max. So it only found quartz, and it found 100% quartz. But let's go to, if you just look at this, it fit this pink line to the black line that was the observed data. And this is this thing up here is the least squares refinement. So these are the residuals left after doing the fit. And that's a pretty good fit for 50 seconds worth of data. So that's definitely quartz. No doubt about it. Now let me show you one more thing here while we're at it. I want to show you what the actual sensor looks like in here. Let me show you what the sensor that collected all the data looks like. And I can show you an image of that. So I'm going to download now let's see, I'll download a single 10-second image, 002.tiff, looks like it's called. And I'll say save it. Save it to the desktop. And now I have the issue of trying to find it. So let's see, let's open up. This is a program called Image that will show you. You could use Image for your own pictures, actually. It's an image processing program. File, open, and I'll go to details, most recent one. Okay, so this, let me just get this a little bit more contrast on this. Okay, so this is a single. Let's see. Can you see that? Yeah, there. You can see it on the screen. So I don't want to turn it around where everybody can see it, but the screen doesn't work. This is a single 10-second scan, and the center of the undiffracted beam is here, and these are these rings. And this is the main ring of quartz right here at about 30.5 degrees. And these are actual individual photons. So this detector, which is 1024 long by 256 wide, each one of those pixels will identify a single photon, and they'll tell you what the energy of the photon is. So we're looking at individual X-ray photons that are striking this chip. That's just marvelous. It's always surprising to me when that happens. You know, if I had figured this out in 1880, I would have certainly got a Nobel Prize. You know, easy. That's what progress is. This is just an everyday thing now. Okay, so let's see. And I could, just let me blow this up a little bit. And you can see there are actually, these are individual photons that struck the chip. And all of these things are cobalt K alpha. I can see the energy of them somewhere. Let's see. There's the X, Y, and the value. And the value of these individual photons, this is actually in what they call digital numbers, so it doesn't read out in energy. But those are all cobalt K alpha, the energy of the tube. Okay, so let's move on. Let's do something more interesting. Any questions so far?
You said it was going to analyze for 5 hours. This would be one sample, because you talk about how many samples you have. You don't have as many as Sam, and I'm wondering, talk a little bit about the strategy of taking the samples, how often you'll take them,
okay.
how many in the 2 years, and what are you going to reserve for future years?
Good question. Actually, the sample wheel in the CheMin instrument on MSL has 27 empty cells, and those 27 empty cells can be dumped and reused. So we have 27 pristine analyses in an empty clean cell, and then we can dump that sample and reuse it. Sometimes you might have a sample that just gets stuck in there, and that thing is lost. But yeah, we vibrate it and turn it upside down. Oh, sure. Yeah, the wheel is about the size of a pie plate.
How is it in the instrument?
It's vertical. It's vertical, and it's analyzed at the top, and the funnel comes down. The analyzing cell is at the top, and the beam is up here, and so it vibrates, does the analysis. The CCD is here, and then when we're done with this, it rotates 180 degrees, so it's upside down, and there's a sump down there, and you vibrate it, and the material comes out. And then we're ready to do another analysis.
Can you tell if you have successfully dumped the sample or not?
We can tell after fashion. We can rotate the cell back up. We can do some analyses and see that we only see clear windows, just the polymer windows, and no material. Now, the caveat is if there's stuff stuck in the corners and stuff, well, we don't see that. Now, there's a way, and so there's a potential for contamination in a cell that we reuse. Now, there's a strategy for fixing that, and basically it's sample dilution. What we do is we take a used cell if we want to renew it, run it up to the top, and we have the ability or the option to take up to 3 aliquots of material from the SASPA system, one at a time, vibrate them, turn it over and dump it, fill it up, vibrate it, turn over and dump it, and hopefully by doing that we dilute the contamination with the sample we're going to analyze and then dump it. And we also have what we call a sample shunt. It's just basically a big hopper that holds material, and if we think the funnel is contaminated, we can pour stuff through the funnel and dump it, and pour stuff through the funnel and dump it. So we have ways to kind of clear the machine of contamination. Now, none of this stuff is perfect. I mean, it's really, I'll tell you, the high ground is trying to deal with dirt. You know, how do you do it? So that really is, you can make really fancy machinery, but just trying to transfer fine-grained material from one place to the other is really tough. It's really tough. Exactly, yeah. And we have a little bit, well, I mean, when we saw the results from Phoenix, everybody had a powwow. And the idea was, you know, we don't know what's going to work if we get in a situation like that. But Gentry Lee, who's one of the big gurus on the committee that was reviewing us, or the whole mission, basically said he wanted as many knobs and dials on this thing as he could. So we would have things to twist and change to see what we could change to make it work. So, but we don't know, you know, nobody knows what when you go to some new place, you don't know what you're going to find there. So and we're very worried about clogging something.
Yeah, you should be, because
yeah.
of Phoenix, it was a major
exactly.
issue.
Yeah.
And you know better than I did.
Mm-hmm.
I followed it closely, but
yeah.
I'm sure you were intimately involved
yeah.
in it. They took the huge samples,
mm-hmm.
which I thought, because I'm a chemist, I thought they were too huge and too big.
Yeah.
And I hope you're going to avoid that, or what are you going to do to avoid taking giant samples that aren't going to go through that filter? And overly large samples.
Yeah.
Maybe I thought they took overly large samples, actually.
Well, I took the cowardly route and figured it was the SASPA's business. Whatever they gave me, I could handle. But the reality of it is, everybody's worried about that. And the first samples we take, we've got an observation tray. They can pick them up, throw them on the ground. You know, the SASPA system could process some material and then pour it on this observation tray. We can use the hand lens instrument, Molly, to look at it. You know, many things. We really don't want to make the mistake of clogging something, because that would be seriously bad.
You can dump that filter then.
Oh, this
right?
one, yeah, yeah. And they do the same thing. You know, if
Dump the whole thing.
Yeah, just go like that. And I don't know if, well,
I
let's see.
mean, the sample is going to be sieved through there, but then what's left you can dump out.
Yes.
How does that work?
I actually don't know. I mean, they have, it's a clamshell system. I haven't seen the Chimera system actually dump samples, but they have the ability to scoop material, sieve it, and they can sieve it to 2 dimensions, to 1 millimeter which the SAM instrument can take, and to 150 microns, which the SAM instrument can take and I can take.
And that brings up another question. Sorry to ask so many questions. Are you going to take some of the same samples for SAM and CheMin and analyze both of them?
Yeah. In fact, that's the one thing. I mean, I talked about how mineralogy is going to tell you the environment. Well, it also tells you. I mean, there's no context for an organic measurement without knowing what it was in, and so the CheMin instrument is going to provide the context for the SAM measurement. So, and it's really critical that we get the same sample.
So you're actually going to get the data back from CheMin first? Is that what you're saying?
That's to be decided. No, it's no. I mean, it's going to take some pondering to figure out what we got. But the plain fact is that CheMin's going to take probably one night of analysis to get a result, and that's going to be sent down. The SAM instrument, depending upon what kind of analysis they do, that could take 1 or 2 or maybe even 3 days. So we can't possibly do the analyses at the same time. We'll have the same material, and after that period of both things being analyzed, then we have to sort it out.
Yeah, no, what I meant was first you'll look at the sample by CheMin, get the data, and after that, then put it into SAM. That's not at the same time, because it wouldn't make any sense. Then you don't get the context.
Yeah, certainly that will be done. But at the same time, well, let's see. I think unless it's very clear that this is not an interesting sample, the process of drilling and sieving and all that, and stopping at a rock, doing everything else, and saying, okay, this is important to drill, drilling it, having the material, and sieving it. That's a multi-soul thing. And I think once we get to that point, we're going to analyze it. I think there was a lot of thought going into this is important. And so at that point, it's probably going to be an automatic unless we think there's going to be some kind of clogging or jamming or a reason why we shouldn't do it. So
Ken Kramer from Spaceflight Magazine didn't identify myself.
Okay,
sorry.
okay. Yeah,
so let someone else ask a question.
Okay. No, that was, no, I mean, we're worried about this all the time, Okay, should I tell you what, why don't I move on? Well, okay, I'll do the equivalent of this is the great thing about being on Earth. I'll do the equivalent of dumping a sample and show you how easy it is. So first of all, if I turn this upside down, sample stays. Sure, yeah. Yeah. So these are 2 plastic windows, and the plastic windows are 150 or 170 microns apart, and the sample in this cell, the sample feeds through that little hole there.
From up here.
From right here. I just dumped it in right there.
Oh, now
and let me show you what it looks like. Well, as long as we're here, I'll show you what it looks like when it's shaking.
This is much better to look at it up close.
And you can see that it's moving.
Oh yeah.
And we have the ability to do this really strongly or in all kinds of different ways if we have
And how long will this be going on?
This will be going on Mars as long as 10 hours. But I think that's a very conservative thing. I'm thinking we'll be able to do things in 3-4 hours. And that's called chaos mode. We're worried about, you see that when you just do this pulsing thing, things start to segregate out, just like, if you have a can of mixed nuts, the big ones wind up at the top. They sort themselves out by jiggling. And the chaos mode just really shakes it strongly and tries to homogenize everything again. So, okay, now let me show you this deal. If it's upside down, well, not much is coming out, right? But watch what happens when I vibrate it. So that's why vibration is important.
Yeah, it is.
And you know what? I'll do this test. I'm going to make. Okay, I'm going to grind up a clamshell, and I didn't do anything. I didn't try and clean this out. I just turned it upside down and shook it. So yeah, so what I'm going to do is I'll put the next sample in and analyze it, and we'll see how much quartz is left, okay? It can get stuck. And we have my colleague Dave Vanneman is on this special team called the, I don't know what it's called, but it's like the really horrible materials team. And they're analyzing literally stuff that we know is horrible, like ice chips mixed with dirt. Yeah, and that's one of the ones we're going to look at. Yeah.
You might find.
And we literally don't want to look at that. I would suggest we can't look at that because this actually will work with liquids.
Well, that's why I'm asking.
Yeah, I've done liquids, and in fact this works with grease, but you have to clean it out afterwards.
Right.
You know, and I don't want, and I can use other cells, but I can't use other funnels. I only have one. So we would do everything in our power not to get a sample like that inside our system.
So when you put something on your table, your observation table, can you take that sample and use it again?
No.
Okay, because
No.
I was thinking it would just sublimate, and then you wouldn't have to worry about the water anymore.
True. One of the things we thought about, we've really thought about this a lot. One of the things we've thought about is, so you drill and just throw everything on the ground and look, or on the observation tray, see what happens, and if it's the kind of thing you want and you can sublimate the ice, or if that's what it is, then you can go back with the scoop and take some of the stuff that either that was residual around the hole or that you dumped on the ground and scoop that up. But we really don't want to have a one-off. You could call it a less than nominal collection. We don't want that. Yeah. Okay. Let me. So we're going to do two things here. I'm going to analyze a clamshell, and I'm going to pretend I don't know what it is. And you saw I didn't really clean out the cell. It's right here, and there's still a little bit of quartz left in there. Now we would actually dump and fill a couple of times to clean out the contamination. But let's just see how much in this analysis, how much contamination left from quartz. So now I guess I'll do it. This is why geologists are so well balanced, because we really can take out our aggressions yeah, this is our whacker. Okay, that ought to do it. Okay, now let's get rid of this. I'm assuming a lot of this is going to be on the cutting room floor, maybe? Okay, maybe not. Okay, so here's my sieve, and maybe I can, if you want to see what the size is, now's a good time. It's pretty fine grained, but that's actually very coarse for the kinds of analyses that we do. Yeah, it's
So you find it better to have a lot of small particles than a few large particles, obviously.
And
Yeah,
what is this
yeah.
made of?
Oh, this is just stainless steel or brass or
Looks like
something.
stainless
Yeah,
steel in my lab.
Yeah.
Okay.
and I have some really expensive ones that are pure
There-
nickel.
Some of them can contaminate, actually,
Mhm.
but I guess you've done those experiments to figure out
Yeah.
what could come through.
Yeah. Now, so let's see. Okay, so now I'm going to take this material that I smashed and dump it in here. And I'll thwack it. Okay, and there's a lot of material in there from just doing that one thing. So there's probably half a gram, which is way more than I need.
You need a few milligrams,
Yeah,
right?
yeah. So that I did exactly the percussion drill is it just pounds on things and then it entrains the material up the drill stem. So basically doing this is very similar to what's going to happen on MSL. Okay, so now I'm going to take my contaminated ones to use cell and put this stuff in there. And put a little bit of this. I don't need to do that. Okay. Okay, so it's filling up nicely. And I'll put it in here. And I guess I still had the other analysis going, so I'm just going to stop it. So I'll stop that one. Start another one. I'm going to call this one Seashell. Okay, I'd love that. Okay, I call this Seashell and tell it to go. And now let me get it over to where we can see what it's doing here. Okay, Seashell acquiring. And we'll see what happens. Now you're going to see something interesting here. The pattern that shows on here is the raw pattern, what we call the film pattern, just a raw pattern. It's not segregated by energies, and this happens to have a lot of calcium in it, right? It's a calcium carbonate, and calcium carbonate is strongly fluoresced by cobalt, which means it will form a higher background than you saw in the quartz thing. You should see like a mound. Oh, there we go. Okay, so obviously it's not quite as strong a diffractor as quartz, but let's wait for a bit and see what happens. Okay, and let's go over to X-ray fluorescence, and I should be able to show you a lot of calcium. Okay, so this is log scale. So this peak of calcium is actually 1,000 counts, and the background is down here around 3. So that's a lot. So what you're seeing here is this is the cobalt peak. This is the peak from the X-ray tube. There's a little bit of iron here that I think is a contamination from the camera. It's a commercial camera. And this is cobalt, or rather calcium K alpha, calcium K beta. Now this particular instrument isn't very good at X-ray fluorescence because we have a big thick beryllium window on the camera, because this is used all over the world, and if we break vacuum or lose the window, then we lost it. Yeah. So that's there we go. There's calcium. We don't see much below calcium with this particular instrument. Aside from that, you see a little bit of iron, and this is the cobalt peak from the X-ray tube. Okay, let's go back to diffraction. Okay, so you can see there's a much higher background here. This high background is actually that calcium being detected, and you'll see it if I showed you the actual image of the chip. You would see there's a lot of counts that aren't on diffraction rings, and those are calcium X-rays. So no, quartz is fairly low energy. With the MSL instrument, we could. With this one, we can't. Okay, I'll just let this go a couple more times because there's a lot of noise here. And oh, okay, quartz is coming in right there, so we'll see a little quartz. This is contamination from the previous analysis. Oh, that's right. That's right.
Yeah.
You would shake it for a little bit, dump it, fill it again, shake it, dump it, and then the third time you do the analysis. And it's very effective.
You got plenty of sample to do it with.
Yeah, it's very effective. Okay, I'm going to stop right here, and I'll download this pattern, and we'll analyze it. And something you're going to see that the background of the pattern that I download doesn't have as high a background, and the reason is this is called what we call film mode. It's just showing you every photon that strikes the CCD. When I download a pattern, I'm going to download something that's filtered for cobalt K alpha. So it shows you something that only has the energies of cobalt K alpha, which will get rid of that calcium fluorescence. So let me go to Files, and I want to go to Processed, and I want this K alpha MDI. Okay, and open. Okay, so you can see this is one of the advantages of being able to filter, to energy filter an X-ray pattern. You get rid of all that fluorescence. So this still, let's see, I don't know how many 10-second collections we did, but this would be way early for me to try and say anything, but I'm going to do it anyway. Okay, search match setup. And with this much with this much chop down here, the computer always finds weird stuff. So this is why it's fortunate to still have a job. Okay, so there's aragonite, and that seems to fit pretty well. And it didn't find quartz, but let's see here. Let me type in quartz, and we'll see where it is. Okay, and I'll drag that over. So I'll put quartz over here. I'll get rid of everything else. And now I'm going to analyze for those two materials. And let's see. Okay, 2 phases, and go. Okay, so here's what it found. Let me change. Well, it's kind of hard to work upside down. Let's see. I think this is it. No. Let's see. Let me do this. Okay, and this is it, maybe? This is it. Nope, that's not it. This is it. Nope. There we go. Okay, so here's the residual. That's not a bad fit. And let's see. Now I can't find my other thing. Well, I completely messed this up. Let me see if I can find this other jade. Let's try it again. Well, now I can't find the other thing. Looks like I dragged it off the thing here. Oh, okay. Sorry. Okay. Okay. Let me do. Oh, you're right. Let me do one more thing. I want to show you something really cool. Okay. Well, I've shown you a bunch of minerals, and once again, I'm not going to spend too much time. There will be some contamination with the analysis because I don't want to waste time doing anything. Well, I wanted to show you about spin-offs and commercial applications and ways this is useful. It turns out that almost all pharmaceuticals are crystalline, and this is a Bayer aspirin, and you can do analysis of drugs with this. So I'm going to analyze this Bayer aspirin, which I don't know what it is. Yeah. Okay, so let's see. I need to dump this stuff out. This shouldn't take too long.
So, David, you've indicated that your samples are going to be large enough that you'll have to be able to fill them up several times.
Yes.
How large do you expect those sample drill events to be? I mean, are you going to
They will drill as much as, well, I don't know about tens of grams, but maybe 10 grams of material. So it's way, way more time than we need. Okay, there's a little bit of powdered, we don't know what it is. And And it's definitely going to be mixed. Well, let's see. I wonder if I should try and. Well, it's just going to be contaminated a little bit. We won't worry about it. And I'm sorry?
I see a need for an astronaut to blow on the thing.
Oh, yeah, yeah. Okay, so let's do this. Wants to see if he's got good drugs with him? Yeah, yeah. Okay, now I'm going to run this again. And okay. I'll stop this one. And well, I might as well talk one. I knew that I could do this with my instrument, and so I actually I got really interested in malaria drug screening for third world countries, and it turns out that between 50 and 90% of the drugs in Southeast Asia and Africa are counterfeit, and especially malaria drugs. And so I've been working with the Republic of Vietnam to get a database and try and get this into their system for identifying counterfeit drugs. And they seem to be pretty interested in doing it. They've already sent me like 200 or 300 things to analyze. And what I really want to do is I want to make this, it is obviously very simple to operate, and we want to make it real turnkey, just like you would for like a bomb sniffer at an airport security place. Okay, let's see. Okay, and okay, let's see. So this might take, why don't let's let this accrue for a little bit, and I'll just answer questions
So
for.
is this same software available, is that on the rover, or is this data
No,
that's downloaded and then you?
It's what happens is we had a lot of questions about that, and it turned out the best way to do it, the safest way, is we take the raw data. The CheMin instrument collects all the raw data, all those individual frames, and the rover compute element then does an algorithm to make this summed up 2D image, and that 2D image is sent down to the ground, and then we make the 1D scan and do the analysis there. So it could be very turnkey, but we simply don't know what's going to happen up there, and we want to have as much human in the loop as we can without causing problems.
So when you say 2D image, you're talking about the one with the circles on it?
Yes, the circles
diffraction,
those diffraction circles will be sent down, about 10 of those per analysis, so about sums of 1 hour each. 10 of those will come down, and then we'll do the 1D conversion and do the analysis on the ground.
Sweet.
That just saves a lot of wear and tear. We don't want to make the spacecraft do more than we need to. Okay, so let's. So that's there's the pattern. That looks like a pretty good pattern. Let's see if we can figure out. Now I hope this works. Okay, so now I'm going to go to Files. Processed. I'm going to do a film because I don't really have fluorescence here. That'll give me more data. Download. Open. Okay, there's the pattern. And I'm going to put a background on here to get rid of this this background. Fit background, cubic spline. Okay, that looks pretty good. Identify, search match. And this time I'm going with this organic data set. This is 450,000 crystalline organic compounds. It's going to search 450,000 possible compounds. And one of the problems with the database that I use is it's got everything but the kitchen sink in there. And the thing is that pharmaceuticals are like minerals. There's only a few thousands of them instead of 450,000. So we really need to make a database that actually suits what we're doing. You know, why look through the woods when you know it's in the it's just in the shrubs. Okay. Okay. It found 2-acetyl oxybenzoic acid. That's aspirin. So there's an analysis of an aspirin from my aspirin bottle in the hotel, which I used this morning. Yeah. So okay. So let's see. Then maybe can we go to the slides just for the last couple of slides? And I wanted to show you. Okay, this was the next slide. This is what I read when I discovered this thing about malaria pills. And this was in the Smithsonian Magazine a couple of years ago. And I contacted the scientists that they described in there, and I worked with them for the last couple of years. And so that's how I kind of got into it. And this is acetaminophen, and this is actually wheat starch, just normal wheat starch. And that's what they use as a binder for the malaria pills. Next slide. This is called Metaplantex. It's one of the and the thing about malaria drugs is there's only one miracle drug left, and if it's abused, then there will be resistance to it, and we won't have it. That's why it's so important. So this shows you a quantitative analysis of this Metaplantex pill, which was supposed to have 17% of artesunate, which is the actual active ingredient, and I wound up finding 15.5%. So that's not too bad, and it basically suggests this is a good pill. I think that's it. Next slide. Maybe that's the last. Okay. Okay, good. Okay, well, so that's it. And oh yeah, thanks. It's.
Can you show us where on the rover, if there's a diagram, maybe on the booklet there, where is the instrument?
Okay, it's inside the box. So
Where inside the box?
If you
front
look at
or the back or
it's
middle
in the
or-
front, and if you look at the top front deck, there are 3 covers for funnels. Now there's on one side there are 2 funnels. That's SAM, and the 2 funnels are the.
Oh yes.
And then the one funnel, and actually in the MSL. In the MSL movie, they show you know, the thing goes around and drills a rock and analyzes something. That's the CheMin funnel, and that's the CheMin instrument they're showing. So
Scoop is going to take the sample collected by the drill and dump it in there.
yes,
And it is how wide?
the funnel
Couple of
is
millimeters.
about yay big, and it has
okay.
it has about a 3 millimeter diameter portion that goes down to where it drops into the cell.
Okay, 3 millimeters. Right. Yeah, I'm
And-
thinking of that tiny model, and that's
Yeah.
actually very misleading. Yeah.
Yes.
So the actual mechanical part, the drill bit, you're taking 3 of them to Mars. What's you expect? I mean, how many samples can you drill? Do you expect to be able to drill?
Good question.
those?
They're able to. I think I don't think they expect they're going to wear down a drill. Maybe they will, but a lot of it was just so that if a drill gets stuck in a rock, they're not anchored there for the rest of their lives, you know. So, but they're certainly using them as consumables. So the real question is on Gale. You know, we've got a 20 kilometer ellipse, and we're going to be doing a lot of driving to get to the clay regions which are at the edge. And so I don't know that there will at least be heightened discussions. I wouldn't call them arguments about what we're going to do. People are going to want to analyze every rock they see. People are going to want to just head for the hills. And the real answer is we're not going to be drill limited or sample cell limited in SAM or CheMin. We won't be resource limited for any of our stuff. It's really going to be, there's going to be a lot of driving to get to some of the really good spots. And so we don't expect to hit 75 samples, which was the original requirement for this instrument, but we could analyze 75 samples. And I think SAM is in a similar situation. So I don't think there's any consumable related reason why we're not going to be able to analyze what we want to analyze. It's really just going to be drive versus drill.
Well, you know, when you say 75 samples, it sounds like so few. I mean, are you hoping to get more than that?
No, that's actually quite a few, and the fact is, I mean, I was kind of defending this concept of what I was doing and all this other stuff to somebody who is a real Mars guy, and basically his comment was that the very first analysis of Mars soil that we get, the first quantitative analysis of mineralogy, is going to rewrite the book. So and really, if we wound up analyzing 75 of the wrong things or 75 of the same thing, we wouldn't learn anything. So I think there's going to be a lot of just a lot of huge thought going into, do we drill this? You know, do we drive there? Do we look at this? And with 350 scientists deciding this in a tactical time scale of like 8 hours, it's going to be real interesting to see.
APXS and the Mossbauer on,
Yeah.
on the rovers.
Yeah. Let me stop this. So
You said this is actually the first mineralogical instrument.
That's
I thought
right.
actually it was one of those.
okay, well the let's see. The APXS instrument is not a mineralogy instrument. It just tells you elements. So if you analyze a lump of coal, you wouldn't be able to tell it from a lump of diamond. There's nothing wrong with it. It's a great instrument, and it's provided really useful data, but it's not a mineralogical instrument. Now the Mossbauer spectrometer does do mineralogy, but it does mineralogy of iron-containing samples just exquisitely. And in fact, Dick Morris, who does all those analyses, is on my team. But anything that's not iron-containing, it's just not there. So this will give you the full suite of minerals that are in soils and rocks. Okay. Okay, well, I guess that's it. Happy to hang around if you want to. Thanks.